and exponentiated objects. This is also, this is Landau's theorem that he actually gave. I just deleted some, that's on both sides. So I didn't have so much to explain. And this requirement, or so take categories with terminal objects, products, and these exponentiated objects, this is called, actually I don't want to randomly work too much on the board right now, but this is called, these are called Cartesian closed categories. So the category of simply type lambda calculi is equivalent to the category of Cartesian closed categories. You might have heard before if you heard someone say Landau's theorem before. Okay. So, why do we care about this? So this is kind of the punchline of this lecture series. If we look at Landau's theorem, so the version that I explained to you, I deleted the function types which correspond to the exponentiated objects. I could also delete the product types and the products here. I can also delete the unit types and the terminal objects. And it's still true that the category extensions of the simply type lambda calculus with just the bare structural rules is equivalent to the category of categories. I think we just put like some type formers on both sides, or some type formers and some type formers on both sides, so that it's not so trivial. So there's something there to talk about, actually. But this theorem is telling us that type theory, at least simple type theory, is basically equivalent to category theory. Okay. The category of types and the category of type theories and the category of categories, if you on both sides with a metric structure, are equivalent. Okay. So the moral is that type theory equals category theory. At least simple type theory. And if you want to make it dependent, then there's other stuff you can do on the side. So, like, I mean, the Curry-Howard-Lambda correspondence, often called prior-binding Kolmogorov correspondence, tells us that all sorts of things are the same, right? Proofs are the same as programs, types are the same as categories, or type theories are the same as categories. It's all the same. Everything here can be conflated, and it just depends on what perspective you want to take. Okay, so maybe another moral is that, at least in my view, type theories are formal languages. Right? They are abstract languages that maybe sometimes we implement in the computer. When we use them, things are moving around in the computer, but they're not very concrete. Like, we are maybe proving things, but what are we actually proving things about? Doesn't have any direct connection to the world, the real world. It's just in the computer. So the point is maybe that the category of categories, or let's say Cartesian closed categories, that's the one that Landau actually studied, contains categories of real objects. So for instance, set is hopefully your favorite Cartesian closed category. Any topos is a Cartesian closed category. Category of topological spaces is Cartesian closed. Category of groups is not Cartesian closed, but does have terminal objects and products. So if you want to say that when you're programming in a simply typed language, which maybe not having that often, but if you're programming in Rock, which is a slightly more complicated version of this story, you're proving things about mathematical objects, and maybe about sets or something. You need these categorical semantics to tie what you're doing in the type theory with something in the real world. I put that in quotes first because I don't know what exactly is real, but certainly people have been studying these categories for at least 100 years. And they, this is like the category of sets is kind of like the real place where sets exist. And type theory is maybe a new formal language that we can use to prove things about sets. And we use this kind of theory that I described to connect the type theory with the real world of sets. Okay, so maybe another way that you use this kind of stuff is you can show that certain statements are not provable. So when you have a language in which you can prove things, it's pretty hard to show that you can't prove something. Like you might just not be smart enough, or you might not have had enough coffee. Maybe sometimes you can do some structural induction over the language to show that something's not provable, but that's pretty hard. But it's kind of easier in some sense, and also when you do it provides some nice intuition, is that if you want to show that something's not provable in your type theory, you can exhibit a model where it's definitely false. And there's also one sense in which these categories are kind of more real and concrete. You know which things are true or false often, yes.
What do you mean by a model that's definitely false? Do you mean like an object there that...
So I don't mean a model that's definitely false, I mean a statement that's false in the model. So maybe here's an example that can make things more concrete. So you guys learned about monolith type theory last week, and maybe used a little bit of rock, improving stuff about it. You talked about the identity type of it and improving qualities. Yeah, so in the past, people wondered if in monolith type theory, when you have two terms in the same type, and you have two equalities between those two terms, you have like alpha and beta in S equals T, and T. Can you prove that alpha is equal to beta? And these guys live, well, yeah. Can you prove that that there's a term in this time now? Yes.
So are alpha and beta each of type S equals T?
Yes.
Okay.
Yeah, so we have two terms in this type. Can you prove that they are themselves equal, that there's a term in this type? Did we talk about this in the last week? Yes.
I asked if that was the case. I was like, oh, you have two members that have it, and she said, oh, you can't prove it either way or something.
Yeah, exactly. So people wondered about this for a long time. I mean, I wasn't around back then, so I don't know like what their intuition was telling them, but based on the papers, it kind of seemed like maybe they thought this would be true. That you can prove that there's a equal kind of type in this term. And it was only in the late 90s, so monolith type theory and Cock, they kind of got started in the 70s and the 80s. So it was only proven in the late 90s that no, you can't prove that these two things are equal. Because there's a model, the group-weight model, that was originally given by Hoffman and Streicher. The group-weight model, and remember group-weights are special kinds of categories, so it's also relevant, in which you cannot prove this. Okay. Yes?
How did they show that in this other model you can't prove it? Why is it easier to show it there?
Because they basically had a category. They said you can interpret types as categories. So okay, it's like there's all different levels being mixed up. So before I said you can turn a type theory into a category. Now they're saying I have an interpretation where the types themselves are categories. They're interpreted as categories. The terms are then objects. And equalities between the terms are isomorphisms between the objects. And you can, of course, have two different isomorphisms for some two objects. Like, for instance, you can consider it a category of sets, and like the Booleans in there, you consider isomorphisms from the Booleans to itself. There's an identity one, and there's a not. Everything's true to false and false to true. So they're definitely, given like almost any two pairs of sets, many isomorphisms between them, not just one. So they exhibited a model where it's completely obvious that this is not true. And that gives us some intuition about actually what Martin Loeb type theory is describing. Maybe it's actually describing groupings. And that gives rise to the part of a homotopy type theory. Yeah, so people have used this kind of technique to show that, like, I don't know, probably log is good in the middle and other kind of constructivity or non-constructive axioms don't hold in Randall type theory or in other type theories. You find a model that you know a lot about and you understand exactly how everything works. You can show that certain things are not true there. So if you have an interpretation there, it must also not be provable in a type theory. Okay. So maybe the last thing I went through, I would have kind of also the same as the rest of them, that type theory is an internal language for these categories. So we have an equivalence. We describe very explicitly the functor that goes from the type theories to the categories, or the portion inverse that goes from the categories to the type theories. So it takes in a category and it spits out a type theory. And that type theory can be used to prove things about the category, can be used to talk about the category. And so category theorists call that an internal language for the category. Okay, yes?
Question about this. The groupoid model shows that it's not provable that the two identities are equal, but it's also, but that, to show that that would be consistent, do we also is the way you prove that by showing a different model where that is?
Exactly.
Okay.
Yeah, so there's another model in a category of sets, kind of straightforward model that you would expect. And there it is true that any two equalities are equal. So yeah, so we know that the statement is independent. It's consistent and it's not provable. So you can add it or not if you want. Okay, so let's see. Now I want to talk about a bunch of like random things that connect category theory with other things that you have learned about. I'm kind of wondering what I should pick and choose here. Maybe actually I'll ask you guys. Okay, I have sections entitled inductive types, algebraic effects, we're really trying one called partial computation, abstract interpretation, and linear logic. What do you want to hear about?
Inductive types. Inductive types.
Maybe raise your hands if you want inductive types, because I think most people said that. Okay, at least half of people like it. Okay, so the point is maybe that like everything, at least like everything I've heard this week, can be explained categorically. And maybe especially I want to mention the abstract interpretation stuff. So there was a lot about posets. Posets are the same as thing categories, or equivalent to thing categories, or categorically equivalent to thing categories. So all the stuff about like Galois connections, fixed point theorems, monotonic functions, those are all poset versions, like thin versions, proof of relevant versions of category theoretic concepts. So that's already very category theoretic. And I think there's a recent paper that was mentioned in the Slack that also kind of describes abstract interpretation like as a technique. So at a more meta level in a categorical. So like everything has a categorical description. Okay, but let me talk about inductive types. Describe inductive types by talking about hopefully all of our favorite inductive types, and that's the numbers. I mean, it's still the thing that gives us the word induction, I think. Okay, so when you program in Rust, let's say, and you want to define the natural numbers, you have two constructors. So you want to say that 0 is an n, and you want to say successor constructor, it goes from end to end. So I'm kind of writing it already in categorical notation, but it looks pretty good when you write it in rock. Okay, so first thing to note is that this thing is of course equivalent to asking for a map per unit to the natural numbers. So we have these two constructors. And then when we talk about the natural numbers, categorically, like when we give the categorical interpretation of like the whole of rock, and we just look at the fragment where we can do this, we are going to interpret these two functions. So unlike the explanation I just gave about the simple learning practice, now we do have function types, of course, because I'm talking about history and rock. So we have these two functions, but of course are also, terms in the natural numbers, given these guys in the context. Anyway, so when we interpret them, they are literally also morphisms in our categories, so they look the same. So categorically, we ask for these functions. We're now categorically, like we're trying to define the natural numbers in rock, and then we can translate that whole story to a categorical story where we're also trying to define the natural numbers. So we can ask for these functions, which are called morphisms, which are in a category 1. We ask for these morphisms. And of course, maybe of course is the wrong word right now, but of course, this gives us a, oops, I'm going to write unit. This, having these two morphisms is equivalent to having one morphism like this. Okay, because we have, let's remember the definition of coproduct. So we have these two inclusions. Right? And to define a map like this, we just have to say where this part goes and where this part goes. We need a map like this, and we need a map like this. And that's exactly the data that's being provided. We have 0 here, and we have S here, and we can call this 0 plus S. So, now I want to say that, we want to say that N has these constructors, number 1, but also that to define a map out of N, it suffices to say where these two constructors go, right? We can do pattern matching. The N, so the N has 0s, but that functions, it's over there in the rock side, but that functions from N to A correspond to giving the data that you need to give when you're doing pattern matching, right? And that will produce a function as in particular also a unique function. And the data that we need to give to do pattern matching to get a function like this is, well, we need to say where a 0 should go, and we need to say where the successor should go. So it's exactly giving the same structure on A. Yes?
Sorry, so the objects, right now when we're talking, the objects are types. The objects are discrimination geometry, right? So
Yeah, so we're thinking about the, let's say, the syntactic category of Randall theory. Yeah, so the objects here correspond to types here. So this object N is this type N, and this morphism S is this, well, I wrote it as a function, but I can also do it as a term S. Okay. So, the way that we define this in calc says that to define a function out of the natural numbers, you have to do pattern matching. On 0 and S, you have to say where 0 and S should go. So it corresponds exactly to giving the same kind of structure on A itself. Does that make sense? So we want to corresponds to a guy, what do we call it, Z for 0, from unit A, and we call sigma from A to A. So this is the data we supplied when we want to produce a function like this. And of course, we can do the same trick. So we get a map like this. A map like this is equivalent to having two maps like this. Okay. So now we consider, maybe I shouldn't write this slow. So now I'm realizing that doing unit plus something is occurring a lot. So I want to package that up because I have applied like a type, like I have kind of functions that takes in a type A and returns type unit plus A. And I've also applied that to n, because from n to unit plus n. Yes.
We can call it maybe.
Yes, exactly. So we want to consider the functor maybe that takes that sends an object A to unit plus A. We talked about last time how this is actually a functor, because to say that it's actually a functor, you need to say also what that's the functions. But it takes an A and produces unit plus A. Yeah.
I'm having trouble with the successor case function being from A to A rather than from N to A.
Well, we want to produce a function like this. So we need to supply like something else, otherwise, if we had to supply a function like this, then we would be done.
Okay. I'm just having trouble with the intuition that the successor case is from A to A.
I mean, maybe it depends on how you define enough numbers in rock, but I think like if have you done pattern matching on your Haskell?
Yeah.
For rock? Yeah, so you need to say where you want to take 0, and you need to say where you want to take, like, you need to say, so you want to define this. So you need to say, maybe also this is now something like aggregation or something like this. So you need to say where you want to take f of 0. And you need to say where you are going to take an arbitrary guy like the successor. So if you have 0 or the successor of n, you need to say where you want to take this. And you can use partial induction, so you can use like, So you can use the fact that like you've already defined it on n, and then you want to have something that takes like your value at n, so you have like something that you do to your definition at n, and this is an A, so what the question mark is
I
the
see.
map from A to A.
Okay, because the recursive part is it's from function of N to where. Okay.
Yeah.
Yeah.
Yeah, I mean, okay, in rock and in agda, you can also use n,
Yeah.
but that's because of dependent type theory, and I'm kind of aligning some details, so it's a dependent type theory, so it has a stronger inductive principle. But I'm not talking about a relatively simple inductive principle for the natural numbers.
Right.
Yeah, any other questions? Okay. Right, so we want to consider this functor because we like use it a bunch of times, so it's probably good to maybe think about it clearly. And in particular, we thought about, okay, if we apply the functor to A, we want to map here to A. If we apply it to N, we want to map to N. So we want to define now a new category. I mean, what we want to think about is we want to think about this thing. Now think about this as a thing. An important thing to our hearts. It's important to our hearts, okay? And when things are important to us, and we're category theorists, they are objects in a category. Okay? So there's now going to be an object in a category. So we're going to define a category of maybe algebras. And its objects are objects. Pairs. Okay, let me write a, little a, pairs like this, where a is in the objects of our category, so let's just call our category C. It could be a C of an LPP. So the pairs are like this, where A is an object, and A goes from maybe A to A. Yes?
Intuitively, I have trouble with something that takes you from maybe A to A. Because like in Haskell, I can't just take it from maybe A to A. Because I can't unconditionally like produce an A. So I feel like I'm misunderstanding something.
You can. Yeah,
I
you
think
can.
it's
Okay.
You have to
Like-
define something for none and something for just.
I mean, this is maybe N, and there's definitely a map like this, where you take the nothing to 0, and this guy to 0.
Okay.
Okay, so let me give this a name. So these are, we call them algebras of this functor maybe. We call algebras. And morphisms so we need a morphism between something like AA and something like BB. So they are morphisms, or they're functions in our category, which is the second category of Randall theory. They're morphisms A to B. This is called F. So morphism F from a pair like this to a pair like this consists of a morphism F in the underlying category, because A and B come from some underlying category, which really is the, in this example, the syntactic category of Randall theory. And we need something that involves a little a and a little b. So it's just going to be a condition. So such that, did I use it first? Such that if I do maybe a, and add it to b. So remember, what we talked about last time, this should do nothing to unit, and it should do F to A to turn A to B. Yeah.
So is every combination of an object and one of those morphisms in the culture category, or are there only some A's here with some functions?
Yeah, so when I write something like this, I mean that the objects are all the pairs of an object in C and a morphism from maybe this object to itself. Yes?
I'm a bit confused. Where does the C come from?
Sorry?
Where does the C come from that the object come out of?
So the C is our ambient category.
So it's like
And-
a category of maybe algebras in C.
So I'm defining the category of maybe algebras. So I have a category C. I have a functor going from C to C that is maybe. Yeah, so maybe goes from C to C. And now I'm defining a new category of maybe algebras. And to be somewhat precise, because I haven't defined this, and it's hard to define, maybe C is the syntactic category of Randall type theory. Since this is doable in Randall type theory. Or maybe the category of Haskell, which doesn't really exist, but. Okay, makes sense so far?
Wait, sorry, you said maybe C is this, but was that maybe a maybe? Did you mean perhaps C is a category in mind?
Yeah.
Oh.
So I'm being vague about this category, C. And it could be the syntactic category of more low time theory, or like the category of Haskell, which is, what is this? Category. Something like that. Okay. Right, so we have enough from A to B, and we want some diagram to compute that's going to involve F, little a, and little b. So I can do F from A to B. I can do F basically from unit plus A to unit plus B. I just tack on this unit and do F, let F do its thing. And then here I have little a, and here I have little b. And that forms a square, which is very reasonable to ask to commute. And why is it reasonable to ask it to commute? Having an object of C, capital A, and this algebra structure, I'll call it, little a, I can think of as endowing A with some kind of structure. Okay, I have some kind of structure, little a. It tells me what the 0 of A is, right, where I said the inhabitant of unit is giving me a 0, a special object of, a special element of A. And if I think about the part of this map that is just this successor, so I can just think about, just ignore the unit for a second, and have a map from A to A. That's telling me what the successor is on A. So it's giving me some kind of algebraic structure on A. Okay, it's telling me that there's a special point, and it's telling me that there's this unary operation. Yes,
So can you have many A's for one A?
definitely,
Have many real A's for one big A?
definitely. Yeah, like you could have in natural numbers, you could let the successor be the same, and you could choose any natural number actually as a 0. Yeah, yes.
Perhaps this is a silly question, but unit is just the unit category, right? Or-
So we're in our category C, so unit lives in C.
Okay.
And so unit is a terminal object
Yeah.
in C. And so if C is the syntactic category of Randall type theory or something like Haskell, then it's the unit type.
In C.
But it comes from the unit type in our type theory,
Yeah.
and then our category is the object that comes from that type, which is also the terminal object in the category. Yes.
Do you need like some sort of maybe B to maybe A thing? Or-
Yeah. Well, I mean, I can produce it.
Wait, but those are all maybe, that's maybe A and maybe B, right?
Yeah.
What about the, like it seems like if you post compose F with A, then you'll have maybe A to B. So how do you get to